the others. So the whole idea here is all of you are attending the class in person, so you can actually get to talk to each other and then know each other. So some students actually have commented that they could not see their groups. So if you actually went on to Canvas, and then under group, you should be able to see something like that. You should be able to see group CA group 1 all the way to group 31. So there's and then all of them are locked except one group. So when you click on the unlock group, that's the group that you have been assigned to. So from the help, I reported the problem to the help desk, and then the help desk say that the student, I should inform you guys that you can actually view and interact with your group mates via group on the left-hand global navigation menu. You can do that, and then there's actually a wiki page on how the interaction, how to actually use the tools. So for those students who have problem accessing, who have a problem seeing your group, your assigned group, please lodge a report to the student help desk. So this is the link for lodging the report to the student help desk. So please click on. I'll post this. I'll upload this onto the Canvas, and then So if you have problem with using the Canvas or the group assignment and so on, please go to here. So over the weekend, there are 3 students that actually have emailed me. So 2 of the the CIT, the CIT staff, technical support staff, he have helped 2 of the students to lodge, but one of the students, he couldn't do that. So but regardless, if you have problem with the IT tools, please contact the student help desk. And then if you have issue with your administrative matter, please contact your department, your respective admin staff in your department. I guess so they will be they are in a better position to actually advise you. So I mentioned earlier that there are altogether 31 group. So these are the randomly appointed leader of the group. So if you are the leader and the other group member no one have actually initiated a meeting, so maybe you can take the initiative to do so. I'll be uploading this onto the NUS Canvas. So altogether there are actually 31 groups. And then the last group will only have 2 students. I believe the project can actually be done by 2 students. So of course, I will take into account that this project is actually done into 2 students when I do the grading. So there will be, it's very likely that I will do the grading on myself, so instead of TA. Okay? Any question on the grouping, on the group assignment and so on? So if you have issue with the group assignment and so on, please lodge a report to the student help desk. Okay? Because I actually checked with some other students, they are all right. So I guess it may only affect a portion of the student. Any question on this assignment? So for those who come late, if you have any problem with the Canvas, with the group assignment for your CA, please lodge a report to the help desk. Okay. Since we are on the topics of the CA, the computing project for the part 1, instead of waiting after the lecture, then I talk about CA. I'll talk the CA. I'll review the CA now. So part 1, there's actually 2 assignments. So the first assignment is a computing project, and then the second assignment is a take-home assignment. So the take-home assignment, I will brief you on how to do it. it should be done on something called an exam solve. So I'll be meeting the IT person that's actually handling the exam solve. So the part 1 CA is essentially a computing project on robot simulation. So the first task involved an independent study of the Universal Robot UR5E as a group. So Universal Robot is a company. The UR5 is a robot from the Universal Robot. It's a commercial robot that's actually pretty widely that's actually quite widely used. So there's actually a physical robot in E201 Control Mechatronics Lab. So if you are based in that lab, you might have already seen the robot. If you have not seen the robot, you may actually go to the lab and take a look at the physical robot itself. This is the robot in the lab. So the robot in the lab, and then I have also uploaded. You can refer to the product fact sheet of the robot. So this is the product fact sheet. So this is a product fact sheet of the robot. So it's actually detailed the range and etc. of the robot. So if you actually look at this robot itself, the robot at this position is actually known as a 0 position. So, but what happened here is the fact sheet itself actually does not include the dimension of the robot. It does not include the dimension of the robot. For example, from here to here, what is the link length and so on. You can go to a physical robot and do the measurement, but the dimension has actually been published. So I'm actually taking this, took this from a book. So you can actually look at this, and then it actually detail the dimension. So it details the dimension, meaning that the link length, the link height. So for example, H1, W1, L1, and so on. So this is the link dimension, and then this is the 0 position. So there's actually a lot of literature on this UR5 and UR5E specifically. So you should be able to find a lot of material on it. So it's nice to look at the product sheet of the UR5E. So and then with that you model the manipulator using the classical DH representation of UR5E. So I want a classical DH representation. So there are two commonly used DH representation. One is classical, the other one is modified. And then there's also one more third one which is actually lesser used. So I mentioned earlier that there's actually a lot of literature. I mean, the UR5 have been studied very widely. So please come up the DH representation on your own. So if you actually copy the representation from literature of some prior work, they may not be using classical representation, and then it will be pretty obvious. Okay, please do your own. You do the model, do the kinematic model of the manipulator on yourselves by yourself, which is not difficult. You should derive the forward kinematics. The forward kinematics meaning that you are actually given the joint input, you're going to determine what will be the final M effector position. We'll talk about the forward kinematic later in this class. And then, so you have to do the part 1 and part 2. And then after that, you should write a program to move the distal. The distal meaning that is actually the far end of the robot. So I make a mistake in my earlier in my file that I actually upload onto the canvas. If I'm going to move the near end the proximal, which is actually referred to the near end, there's actually little meaning of it. So I want to move the far end. So meaning that the last link, the end effector, to draw the workflow on an arbitrary work surface. So you can actually imagine any work surface, and then you should draw the workflow. You should start from the 0 position of the manipulator. So if you actually look at this, if you look at the fact sheet over here, this is the 0 position of the manipulator. So when you say 0 position, meaning that all the joint angle is having a value of 0. So the theta is actually equal to 0. We'll talk about the joint parameter later. So you should start it at point. So you should start it from the 0 position of the manipulator, and then pause at the beginning and ending of every letter. So there are 4 letters altogether. So you pause and start writing the letter. Okay. So F, you can actually move up, back, and then a second stroke and so on. L will be easier to write, so it's basically just one and then another perpendicular line. So you have to make sure you actually pause at the beginning of every letter, so that you continue with that. And then you should define the letter, the speed at which the letter should be written. So to draw the speed at the speed, meaning that when you actually draw the robot F, you should draw it at the speed that you specify. And then you should complete the writing of the letter at the speed you specify. And then the writing of each letter should be completed within the same time. So meaning that if your simulation is going to take 10 seconds to complete the writing of F, you should take 10 seconds to complete the writing of L, and you should take 10 seconds to complete the writing of the O, and so on. Okay. So the 4 kinematic, meaning that you're actually given the joint position, and then you determine the position, the end position, the position and orientation of the end effector. So in this case, you have a F over here. So you can, of course, you can try and error. It's a simulation to achieve the F. Or the other way, you can actually try to do an inverse kinematics, and then determine how you actually write the F. To do the inverse, to control the speed, you probably need something called the inverse Jacobian. So this is something that we're going to talk about. It's essentially a differential relationship. So this is the task, which is not difficult. And then it will contribute 25% of the final grade. The computing project will be comprised of a group of 3 or 2 students. All the code should be written in MATLAB. You are encouraged to use a symbolic Math toolbox. So for example, when you actually derive the equation and all those things, you can actually use the symbolic Math toolbox to actually help you with the deviation. I don't think you need to use a robotic toolbox to complete this CA. So bear in mind that the robotic toolbox may actually use a modified DH notation, and then it's actually not what the question actually asks you to do. So you should upload a zip document to the submission folder on the NUS Canvas by 14 April 2023, Friday, 2359 hours. So 14 April 2023 is week 13. So you can actually finish this, and then after that you can actually start preparing for your exam. The zip document should actually contain this item. It should contain a report. So the report is not going to be very long. So you have 3 students, so probably everyone is actually responsible for about 10 pages. So if that's the minimum, and then I don't think you will write more than 50 pages for this report. And then there should be a cover page that clearly indicate your name, student number, and email address. So in case if there's anything that I need to contact you, I can do so. Please submit only one document. And then the report should also include an introduction, describe your solution for each task, how you actually approach the different tasks. So it's likely that you will, after you derive the kinematic, you probably will look at how the inverse kinematics. You will probably involve deriving the inverse kinematics and then planning the stroke. And after that, you have to determine the speed. And after that, finally, you may actually need to do a trajectory planning. The trajectory planning will be our last lecture. So there should be some capture of your simulation and results. And then there's something that's actually important will be your discussion and conclusion. So you discuss your solution, and then say how good you have achieved it, or how much you have achieved to the problem, and anything that you actually want to comment. You can actually do, if you try different method, you can actually discuss a different method over here. The zip document should also include your program, which is your MATLAB codes. So please have a readme docx on how you actually execute the code, so that if there's a need, I'll be able to run the code. And finally, you should have a short movie or animation of your simulations. So nowadays, so this is a robotic project. So you should show that it actually works. Okay. Yes, thank you.
Question. You mentioned that we should write the flow on an arbitrary surface. Is that surface like a specific surface you give us, like one?
No, you can actually decide on the surface. It could actually be a horizontal plane, or it could actually be a vertical plane, or it could actually be a tilted surface. Yeah, it could be any plane. So you can actually decide on the plane that you actually want to write the word flow. Yeah. So from the screen cap and from the video itself, I'll be able to see whether you did actually write the workflow. So you should pause before you move on to the next letter. So how clean is your letter will actually be quite useful. Okay. And then the file name of your zip program should be your group number. So everybody have a group number there. Any question? Straightforward. It's not very difficult. You work as a group. And then if you actually need to see the robot yourself, you can go to control lab. There are actually two robots side by side. One is actually a UR5E, the other one is actually a UR10. So the 5 over here is actually referred to the load, the payload. So one is 5 kg and then the other one is 10 kg. Okay? Yes?
So this simulation is a simplified structure mechanism of the robot, like very negligible thickness.
Yes, you can draw it as a single thin line. I'm going to give some example. Okay, I'm going to give some example on the modeling. So for example, if you build your own robot. So this is a cable buying robot that the student actually that's actually from a project that in cooperation with Samcorp, a shipyard. So what happened here is actually they need to so when you're actually in shipbuilding, they are a very big ship. They actually have a lot of cable, so the power cable and so on. So the power cable will have to go along the ceiling or go along the wall of the ship. So and then those very thick cable will have to be tied together. So at that point in time, there was a project that we worked with them on making this cable binding robot. So same thing. So you have the structure of the robot, and then the first thing that you do is you have to assign the frame. So for example, in this case, the robot will actually have two manipulators, at least more than two pair of manipulators. This is 1 And then this is for the left and right hand of the robotic system for cable binding. And then there's also an actuator that's actually move around here. So, for example, if I'm actually referring to one single actuator, one single arm, so this is one single arm, the first thing that you actually need to do is you have to assign the frame. You have to assign the frame to the joint. You have to label the joint. You have to label the link, and then after that followed by label the joint, and then after that you assign the frame. So you assign the frame, the right hand coordinate frame, onto the link, onto the systems, and then after that you derive your DH parameter. And then after that you have you form the link transformation matrix. So after you form the link transformation matrix, you can. So this is for the left hand. This is for the right hand. Sorry, this is for the right arm. This is for the left arm. And after that this is for the tilt arm. So this is the link transformation matrix. And then if you have from the base to the, if you have the transformation from the base to the end effector itself, you will have the forward kinematics. So you can actually do your magnetic simulation by actually indicating them as a simple horizontal line, simple straight line. So for example, this is the left arm. So this is the right arm. This is the left arm. And then this is the central arm. So you can actually use use a simple line to actually represent them. I don't need you to draw or graphically render the robot, which is not the intent for this project. And then after that you can. So in this case, the student actually draw the structure that the robot will be working on. So this is the robot arm. And then he moved the robot arm, looking at the positions and so on. So this is the bundle is actually the when you bund the cable together, there's actually there's actually a lock kind of mechanism. So after indicating the bundle and so on, the robot will actually, the membrator will move. So I'm not expecting you to actually graphically render the manipulator. So you can actually simply have them as a straight line. And over here, when you click on the button run, and then the whole execution time start. So you can actually draw it as a straight line. You can also draw it as a rectangular block. So for example, there's a manipulator over here that's actually for needle insertion. So you can so instead of having straight line, you can actually draw vertical block. You can draw bar, rectangular bar, or even circle, or even cylinder if you actually want to. So it's depict. So like for example, the starting position, and then after that the movement of the manipulator, and finally at the specific position. Okay. So don't spend time on the graphic rendering. It's not important. Okay. So of course, MATLAB is not the only simulation environment that can actually support UR robot. So for example, UR robot actually they have something called UR sim, which is from the manufacturer. So the UR sim will actually enable you to do the simulation, and then after that, do offline programming of the robot. So the purpose of this study is that if you translate this thing with the simulation, you can actually do offline programming of the robot. Sorry, the UR sim for offline programming of the robot. UR sim, URSIM. So it's actually proprietary from the UR robot. Okay. Any question?
So for the UR family, is
Oh, the UR5E is only one. The UR5E, if you actually look at the fact sheet itself, this is the UR5E. So it's a single manipulator. So it's a manipulator. So at the end, this is the last link. There's no end effector attached. I mean, there's no clipper or anything attached. So you may specify a specific point ahead of this. You may take the final point as a point to draw your character. You don't need to model the clipper and the tools. Okay? Thank you. Understand? So bear in mind when you actually do the simulation and all those things, the fact sheet actually tell you the degree that they can actually bend. So this is kind of important. So you need to study the fact sheet. Yeah. So for example, if you actually look at the fact sheet itself, the UR5 or there's actually the UR5E is the latest, is one variant of the UR5. The dimension wise they are very much they are the same. The period will actually tell you this is 5 kg. This is the reach. So the reach is 850 mm. So you know the reach, then you should know that your plane should not be too far away. Okay. And then there are other parameters, the force sensing, and then the working range for the robot. So you bear in mind the maximum speed. Okay. Okay. Any question? Any other questions? Simple assignment. Yeah, I think it should be it should be fun because you just stick the robot and then do a simulation that probably will actually apply what you have learned throughout in this part of the module. Okay, work in group. So I'm not going to award different mark to different person. Okay? Okay. If there's no question, we continue with the lectures. So today we aim to finish the remaining part of the chapter 1, kinematics. So what happened here is before the break, we actually gone through the first 3 sections: the position, orientation, and coordinate transformation, homogeneous transformation, as well as other orientation representation of other orientation representations. So the 1, 2, 3, the section 1, 2, 3 actually provide you with the mathematic tools for our subsequent study. So the 1, 2, 3 are general, are quite are essentially applied mechanics in nature. So now with the tools that we actually have studied, we move on to study the kinematics of a robot. So when we look at the kinematics of the robot, the kinematic is essentially the first thing that we actually need to know about the robot. So you need to know how to place the end effector as a specific location in space to forward or inverse kinematics. So I'll be going through this. So I'll be talking about the kinematic modeling of the manipulator arm. So in this case, we will be using the classical DH notations. Typically, I'll talk about the forward or direct. Forward and direct. This forward kinematic equation is also known as the direct kinematic equations. And after that, followed by inverse kinematic. So this is what we're going to cover. And then next week we'll actually move on to statics. And then next week we actually want to, because what happened here is we want to move the end effector in a specified direction at a specific speed. So you need to coordinate the motion of the individual joint. So the end effector position and orientation are directly related to the joint displacement. We could actually derive the differential relationship between the joint displacement and the end effector location, and then solve for the individual joint motion to achieve the coordinate motion. So this will be the topic for next week. So when we talk about the differential relationship over here, is a Jacobian matrix. Okay, so we are interested in we want to model we want to do a kinematic modeling of the manipulator arm. We are interested on this. We are interested on in our context on classical manipulator. We are interested in a manipulator shown over here. So this is essentially a so-called open kinematic chain. So it's a serial linkage. So that means one after another. So we have. So for this serial linkage itself, for this manipulator itself, there's always a base. So most of the time, we actually assume that the base is fixed. And then we have an end effector. So the end effector, and then and then followed by the end effector, and then there's a two. So this is also known as the two position. So what really matters to us is we want to express the end effector position and orientation with respect to the base frame. So this is the base frame. So this is a base, this is an end effector. So this is the furthest end of the robot. So we want to express this end effector position and the orientation with respect to the base frame. So in other words, we want to find the functional relationship between the end effector position and the joint displacement. Because the joint displacement itself will actually determine the final end effector position and orientation. So if we are to properly define what is a kinematic modeling, a kinematic modeling will describe the spatial position of the joints and link and the position and orientation of the end effector. So when you are tasked to do the kinematic model itself, you will have to do all this. So this is an overview of the method. So the first thing is you actually look at the robot manipulator, and then you have to identify the link. Identify the link, and then as well as label the link. So you will label the link number in series from 0 for the base. So this is link 0, link 1, link 2, and so on until link n. So link n is essentially your end effector. And then this point is your two position. So this is the first thing that you do. You have to label the link, and then after that you have to identify the joint and label the joint. So the joint will actually be defined between the link I minus 1 and link I will be actually be labeled as the joint I. So for example, in this case, this is link 0, this is link 1. The joint this is known as joint 1. So this joint 1 is actually in between the link 1 and link 0. So same thing, after you have identified the joint, the next thing is you have to label the joint. So you label the joint as well. So after you have done that, the next thing is you want to attach a coordinate frame. So the coordinate frame is a right-hand Cartesian coordinate frame to each of the link. So to each of the link itself, you have to attach a coordinate frame. So you attach a coordinate frame to each link of the joint. So each link of the joint have its position, x, y, z, as well as its orientation. So you need to attach that. And then finally, you use a 4x4 homogeneous transformation matrix to describe the position and orientation of the joint between the frame, the current frame, and the next frame. So for example, you will define a transformation matrix between the frame link 2 and link 1. Or coordinate frame 0i, 0, 1, x1, y1, z1, and x2, 0, 2, x2, y2, z2, and 0, 1, x1, y1, z1. So you need to have these transformations. So the n effector homogeneous transformation will essentially be a consecutive homogeneous transformation from the last frame back to the first frame. So this is what we have learned earlier. So we look at how we should actually, so after we have labeled the link, and then identified the joint, the next thing is we will have to attach the frame. So we attach the frame. So every frame is essentially a coordinates. So remember what we have gone through last week. So you attach a frame to the base, to every link, to every single link. The question here is how the DH notation itself will actually teach you a systematic method of actually describing the kinematic relationship between the adjacent link. And then based on the 4x4 homogeneous metric representations, what happened here is useful because it's actually use the minimum number of parameter to describe the kinematic relationship. So how we actually attach the frame matters, and it's not too difficult. So it's after a while you will get used to it, but you definitely will require practice. So we need to attach the frame OI, XI, YI, ZI onto the link I. So we take apart. Since we are actually focusing on how we are going to attach one specific frame, we don't need to consider the whole entire chain. So we only take out the link I as well as the link I minus 1. So first you have to determine the origin of the I coordinate frame OI, which is actually located at the intersection of the joint axis I plus 1 and the common normal between the joint axis I and I plus 1. So first you need to identify this. This is the origin. And then this is the joint axis I plus 1. So every joint is a single 1 degree of freedom device. So 1 degree of freedom, you will only have one single axis of movement. So you can actually, so for every joint itself, you can identify there will be an axis. So this is the joint axis I plus 1, and then this is the common normal. And then after you have identified the origin, the next thing is you actually need to determine the XI axis. So the XI axis is actually directed along the extended line of the OI is the origin. It's along the common normal, so it will actually be directed along this direction. And then after that, you have to determine the z-axis. The z-axis is probably the simplest to identify. The z-axis is always along your joint axis, always along this joint axis. We mentioned earlier that every joint have a single axis. So with that, you will be able to easily identify the z-axis. So after you have your z and x, you can actually determine your y according to your right-hand coordinate systems. So this is known as the y-axis is chosen such that the resultant frame OI, XI, Z, YI, ZI, ZI form a right-hand coordinate systems. So a right-hand coordinate system from left, from x to y, you will have your z pointing out. So same thing over here. You are given your z, you are given your x, so you know that the y will be where your finger going to turn. Okay, so this is, or you can actually do this. Okay. So you have your origin x, y, and z. So you define the frame. So from the frame itself, from the coordinate system that you actually attach, you can actually identify 4 parameters. So these 4 parameters are important. So it's minimum because there are 4 parameters. So the first parameter is the angle between the xi minus 1 axis and the common normal measured along the z minus 1 axis in the right-hand side. So you have this angle if you have a revolute joint. So the theta 1, theta I will be there if you have a revolute joint. And then the di is the distance between the origin OI minus 1 and point HI. So this is again mainly for your this one will be for your prismatic joint. Then you have the length of the common normal. So you have this length of the common normal from here to here. And then after that you have your alpha I, which is the angle between the joint axis I and z axis in the right hand coordinate. So right hand side is important because the right hand side defines your positive or negative. So these are the definition, and then as you practice more and more, it becomes very straightforward. So bear in mind that you have. So what happened here is if you actually look at this, the di and theta I are variable. So you either have theta I or di because you only have one single degree of freedom. And then the ai and alpha I, they are essentially fixed. So the ai is known as the link length. It's the shortest distance from the axis I to I minus 1 to I along the common normal. So this is the link length. And then the alpha I is actually known as the link twist. So it's the angle from the projection of axis I minus 1 to axis I on a plane perpendicular to the common normal. So you have a projection, you move it over here. So for example, this projection moves over here and then you find the angle. Okay, it's a way to look at it. So the alpha I and ai are essentially constant parameter determined by the geometry of the link. So they are constant. So there are 2 constant and 2 variable. And in almost all cases, only one variable is actually in effect. Okay. So the variable joint, so you have di if the variable joint is prismatic, and then if you have theta I if as a variable if the joint is revolute. So this is the drawing of the link, and then if you actually remove the link and then focus on the frame, you have something like this. This is joint I, this is joint I plus 1. Okay, this is the coordinate frame OI minus 1 and coordinate frame OI. Follow? It's not difficult. You just need to get used to it. So when I have these 2 frames, the OI minus 1 and OI over here, so typically you have something called an intermediate coordinate frame to tie them together to actually determine the relationship of OI with respect to I minus 1. So you want to determine the transformation matrix I minus 1 IA. You want to determine this transformation matrix. So sometimes instead of writing I minus 1 IA, you may actually come across people write as I minus 1 IT. So they mean the same thing. So you have to look at the context. Okay. So the I minus 1A, the I minus 1 to relate the I the frame I, the OI with respect to frame OI minus 1, you have this I minus 1 IA is equal to I minus 1, the intermediate frame A multiplied by the intermediate frame IA. So you can determine the intermediate frame quite easily. So this is the intermediate frame, and then we can actually arrive at this transformation matrix, this homogeneous transformation matrix. So this is the rotation component, this is the translation component. And then similarly, we can also form the relationship I minus 1 in INT, the intermediate with respect to I minus 1 transformation matrix. So this is the rotation matrix, this is the translation. So after I have this INT, the intermediate IA, and I minus 1 intermediate A, I can multiply them together. This is the link matrix that actually establish the link between each of them. Okay. So you have to do this for your UR5E robot. Okay. So because everything is actually bundled into this transformation matrix, so the order of the rotation and translation actually doesn't matter. So there are some exceptions to the DH notation rule that you need to pay attention to. So for what happened for the last link, the frame M. So the frame M will be the last link. So this is the true position. So the origin of the continuity frame will be chosen at any convenient point of the N effector. So in this case, you choose something over here. So this is along this line, along your x-axis, and then you get at the two position. So the N effector, this is N effector. This is the point where you're actually holding on to the tools. So this is also known as the two position. So you fix your origin over here. The SN axis will intersect the last joint at right angle. So you take this at right angle. This is the joint. This is the axis. You pick a right angle, and then you can. The alpha M is arbitrary from this case. And then you define the Y, or you define the Z. So because you define the Z, it's kind of arbitrary, then you have your X, you have your Y. Okay? So this is the last link. And then of course, your base link will not have O minus 1, so you have to consider how you actually handle the OO as well. So the ZOG axis will typically be along the joint axis. So you start off with the joint. You know very well. You know the joint. So you know that there's a specific joint, and then you know the joint axis, and then you have the ZO defined along that. And then after that, the joint axis is a very good indicator. It's very useful. So it's in every joint, so it's very helpful. So the origin will be chosen at the arbitrary point on the joint axis, and then the SO and YO axis will also be arbitrary. But you have to make sure that you should follow the right hand coordinate form. So in all cases, you have to try to make sure that you have the simplest form of representation of the manipulator. So for the intermediate link, so when the two joint axes of an intermediate link are parallel, so you don't have a common normal. So for example, you have a case like that. So these two joints are essentially parallel. It's not so common, but you may have come across. So in that case, the choice of the common normal will be arbitrary. So you actually, most of the time you actually want it to pass through the origin OI minus 1. So when you actually do that, your DI actually becomes 0. Okay? Then for prismatic joint, the only direction of the joint axis is meaningful. So the position of joint axis can actually be chosen arbitrarily. But they should be done consistently. Okay, this is the procedural assignment. And then we look at one simple example. Very quiet. Everyone okay? Okay, so we take an example. So we use a simple example. So this simple example will actually consist of only 2 revolute joint. So the 2 revolute joint is also, this is also known as RR manipulator. So the R stands for revolute. So RR 2 revolute joint. So you have this first revolute joint and second revolute joint. This is the N effector and this is the 2 position that you identify. So the first thing you do is there should be at least one more frame than the number of joints because you have the N point. And then one frame must be on the N effector. So this is one frame, this N frame is actually on the N effector. So you take care of this one N. And then all axes should be drawn in one of the following directions. So you have your, so if you're integrating something that's actually out of page, so you'll be a circle with a dot. If you are integrating something that's into the page, will be a circle with a plus. So circle with a plus, basically you are actually screwing in, and then with a dot out will be something like that. So you can allocate by the z-axis as the axis of revolution or direction of motion. So when you actually look at this, you kind of know where is you can actually easily identify the axis of rotation. So this is a revolute joint, this is rotating in this manner. So this is the axis, and then this is rotating in this manner, this is the axis. So the axis will actually help you to define the z-axis. So this define the z-axis, you have z0 and z1. And then after that, the x-axis must be perpendicular to the z-axis of the previous frame. So this one, so your x1 should be perpendicular to the previous frame. And then the x-axis must intersect the axis of the previous frame. And then y-axis must be drawn such that the frame will actually follow the right-hand coordinates. So this is one way of interpreting what we have gone through in the procedure. So with that, you will be able to assign the frame. So you assign the frame in this manner. So this is a Z, and then this is X. And then this is the endpoint, one more frame. So one more frame, endpoint. And then this is, you can choose it arbitrarily, but the X2 will probably fall along the link. And then when you actually look at this itself, we actually know that the Y2 probably will be good over here. Okay? So after that, you form the DH parameter table. So over here, if you actually look at this, there's only 2 links. So this is one link, there's another link. This is 2 join, 2 link. So you have link 1 and link 2. So you determine the angle for the theta, alpha, A, and D. So A and D are essentially representing a displacement. Theta and alpha will be representing the rotations. And alpha and A, they are fixed for the length. And then theta and D will actually be are the joint variable. So you have this definition from here. So the angle, so the way to measure theta will be from the previous frame Sm minus 1 to Sm. So this will be the angle in the right hand frame. and then the alpha will actually be measured along the z-axis. Measure along so that the measure will be rotate along the SM such as the Zn minus 1 measure Zn. A is essentially the length of the common normal, and D is the distance between the origin of the point. Okay. So based on the procedure itself, you can actually infer it on a simple experiment example in this manner. We'll talk about the manipulator Jacobian next week. Okay. So once we have all the frame, and then once we have all the frame, we have identified the joints and the link, and so the joint parameter and the link and the joint variable. So the next thing here is you can form the matrix, and then you can form the matrix between every individual link. For example, over here, the AI minus 1 I, the QI over here will represent. It can only have two value. One is if it's actually a revolute joint, it will be theta I. If it's prismatic, it will be DI. So this is the intermediate link transformations. And then with that you can, so this is the end position. You want to determine the T over here that actually link the end effector with the base frame. So you identify the joint variable and link kinematic parameters. So you can denote the joint displacement by QI. So QI will actually be equal to theta I if it's going to be a revolute joint. QI is equal to DI if it's actually going to be a prismatic joint. And then you assign the Cartesian coordinate frame to each of the link. And then include the base 0 and n effector n that we have gone through just now. You can define the link transformation parameters, which is this, the A I minus 1 A I, or the I minus 1 I A. So they mean the same thing. And then after that, you compute the forward transformations. So the forward transformation will be ONT, so meaning that the frame n, which is your n effector with respect to frame 0, which is at your base frame, is equal to 1, O1 we reference to 0. So you have your 0, 1A, Q1. The Q1 can be either theta I or DI, and then multiplied by 1 over 2 A Q2, and so on. So you cancel off 1, 1, 2, 2, and so on. So you actually end up with 0 n. So you multiply all these together, you have the kinematic equation of the manipulator arm. So meaning that if I know the QI, so if I know the value of the theta I, if it's a revolute joint of every joint, I'll be able to determine the GONT. Okay? You're quiet because you have learned this before, or it's new to you. Okay. You want a break? Okay. Maybe let me finish this forward kinematic, then we take a break. Okay, so we take an example. So this is a more complicated example than earlier on, but this example is closer to what you have for your assignment for the UR5E. So bear in mind that when you actually do the kinematic equations, when you do the kinematic modeling, you should have the robot start at the 0 position. Try to have the robot start. I mean, you should have the robot start at the 0 position. So you have the robot side at the 0 position. So this is your robot. The first thing is you identify all the link, you label all the link, and then you identify all the joints. So you identify all the joints, and then which joint, and then you determine which joint, the joint whether it's a revolute joint. So the first joint is a revolute joint. The second joint is also a revolute joint. The third one is a prismatic joint, so it's linear movement. And then the joint axis chosen should be coincide with the joint 4. So you try to plan ahead. And then joint 4 and 5 and 6 are essentially a revolute joints. So these revolute joints, the axis actually intercept at a single point called W, point W. So we'll be going back to this manipulator again. So the point W essentially is your width. So the W is essentially a width. So these three over here, these three joints over here actually define your width. And then these three joints over here define your arm. So after you have done the kinematic modeling, you attach a frame. So you choose a base frame, and then you choose all the base frame from there. Then the base frame was chosen on the table surface. So it's chosen on the table surface over here with Z0 along the axis. And then you have your X, Y defined in the right-hand side. And then the origin of the final frame can be defined arbitrarily, but is the 2 position. So these 2 positions you should try to align. In this case, you actually align with this particular axis. So other frame will actually assign according to the DH rule. So in all cases, you actually try to find the coordinate frame so that there's a minimum number of non-zero parameter. So if you form the table, you should have as many zero as possible. That's what it meant. But there are things that it cannot be zero, but you should have the minimal number of non-zero parameter. So if you go through what we have done earlier on, you will actually end up with this table. So if you have your theta I, which is your revolute joint, so theta 1, theta 2, D3. So I'm actually quite particular about the D and L. So the D3 actually implies that this is a variable. So you have your theta 4, theta 5, and theta 6, and so on. Okay. So bear in mind that the manipulator, when you model the kinematic equation, that the manipulator should be at the 0 position. So you have your 4x4 matrix, I minus 1, I, A, Q, I. And then you can actually substitute them into this matrix. You have the table value, substitute everything into this value. Then you will actually end up with you will actually end up with this value. So you start with the frame 1 with respect to frame 0, A, theta 1, this is a revolute joint. 2, 1, A, theta 2, revolute joint. 3, 2, A, this is D3. So this is a prismatic joint, and so on. So after you are done with this, the next thing here is you multiply them together, and then you will get the final matrix. So to multiply the final matrix together will be tedious. So one way to do it is to use a symbolic max toolbox. So from MATLAB downstairs, you define the variable and then you multiply them, rather than actually you do your manual modifications. So this equation itself will actually represent the n effector position and orientation the 6, which is at the 06, the frame 06 with respect to frame 00. And then it will be a function of the joint displacement theta 1, theta 2, d3, d4, theta 4, theta 5, and theta 6. Okay? Okay, I think we'll have a break. We'll have a 15 minutes break. We'll resume the class at 7:20. Hello class, we'll resume the lesson. Okay, have your attention please. Yeah. Okay, before I move on to invert kinematic, we give a bit more example about kinematic modeling. There's a set of robot called planar robot. So a planar robot essentially is a 2D robot. So you have a plane, so a plane, XY plane, and then you actually move. So you don't have one more set of axis. So the method of the application, the method that we actually describe apply the same. So there's actually no difference. The approach that we're going to take is the same. So and then there's actually, so this planar robot is actually quite useful. There are many applications that you only need to work on a specific plane. So you don't actually need the 3D. The planar mechanism. The planar mechanism is also easier to analyze. So this is known as RR planar manipulator. So it's a planar manipulator. It's on the XY axis, 2 link, meaning that you have one link and another link over here. The RR same thing. The RR here refer to revolute joint. So you may come across a lot of time when you actually describe all the different manipulators with all these terms. So you start off by so this is the planar robot, and then you start off by drawing the skeleton structure. So skeleton structure, this is the base, and then you have one joint. You have one joint over here, and then you have another joint over here, and then this is your end effector. This is your 2 point. So a lot of time you may actually come across something called 2 center point (TCP). So this is a 2 TCP, and then you tend to put your last link over here. So you analyze this, and then after that you do your DH notations. You assign the frame. So you assign the frame, and then with that you actually can identify the parameters, the DH parameter. This is under the standard of classical representations. So after that you can determine in between the link, you can actually determine the transformation matrix. So this is a transformation matrix 01A. So meaning that the origin of the frame 1 will refer to frame 0. So it can be written as 01T or T01 or A01 and so on. So yeah, so it can be written in different form. Yeah, you may come across the different writing in different books. So, but you actually read, so you have to read within the context, and then you know that this is what is it. So you actually, so they actually refer to the same thing. So you define your 01A, 12A, and then after that, the kinematic of the equation of the manipulator is essentially 02T. So it's 01A multiplied by 12A. So you cancel off 1, you have your 02. So this is your kinematic equations, and then a lot of time we use T, but there's no mistake if you actually write it's a 02A. So the 02A is essentially 01A multiplied with 12A. So you multiply the matrix. So you may come across, to be specific, you may actually come across people write 02T bracket theta 1 and theta 2. So this is the parameter. Okay? So you multiply them together. You actually see a whole a complex the different term, sine, cosine, and so on. So I think early on in the class I mentioned that you should remember how you should actually have some knowledge on the trigonometric identity. So these are some of the identity that you actually need to. So this is some of the trigonometric identity that you need to be aware of. So for example, if you did the multiplication and so on, you come across a C12. So a C12 actually implies cosine theta 1 plus theta 2. So when you have cosine theta 1 plus theta 2, C12 is actually equal to C1, C2 minus sine 1, sine 2. Cosine theta 1 plus theta 2 is equal to cosine 1 times cosine 2 minus sine 1, sine theta 1, sine theta 2. So sine theta 1 plus theta 2 is sine 1, 2. It's x12, so it's actually cosine theta 1 multiplied with sine theta 2 plus sine theta 1 multiplied with cosine theta 2. So you have this cosine theta 1 minus theta 2, sine theta 1 minus theta 2 as well. Okay, so this is a set of trigonometric identity that you need to work out. So when you actually have this thing, and then the next thing is actually you move on to with this trigonometric identity, you actually arrive at a simplified form. So this is a simplified form where you have your 0, 2t, theta 1, theta 2 equal to C12 minus x12 zeros, C1 L1 plus L2 C12 and so on. Okay. So meaning that when for your exercise, for your CA, your forward kinematic equation, it should be in his simplified form. Okay. So if you are going to do it manually yourself, it's going to be tough. Make use of the symbolic toolbox. It will be helpful. So with the symbolic toolbox, you can actually insert in value as well. Okay. So this is, so this is for two-link. So when we actually expand to three-link, the same thing happens. We can do we're basically doing very much the same thing. So the RR map, the planar, you may call it a planar 3R manipulator or planar RR manipulator. So there's actually two revolute joint, and then you have this three-link as well. So this is quite. You have quite a fair bit of applications for this planar 3R manipulator. So same thing. You look at it, and then you draw. This is a spherical diagram. You label the link. You label the joint. You attach the frame. And then after that, by attaching the frame according to the DH notations, so sometimes, and then you actually have this, you have the table. So this is your table of the parameters. So you have your DI, theta I, AI, alpha I. Okay, so these two are variable, and these two are kind of fixed to your geometry. So after you have done with this, same thing, you have your 0, 3, the last frame is 3. So 3 with respect to t, you have 3 joints. Theta 1, theta 2, theta 3 is actually equal to 01A, 21A, 32A. So you multiply them together, you have 03A. Okay, then when you multiply and then do the simplification itself, this is what you have. So in this case, the multiplication is important. Make sure you do the multiplication in the order that's actually been specified. You must know the forward kinematic before you can actually work on the inverse kinematics. And then you will find that the solving of the inverse kinematics is you are actually dealing with a nonlinear equation, set of equations. Okay. So now we move on to the inverse kinematics. So the forward kinematic is forward, so meaning that you give the input of the joint angle, and then you move the n effector is moved. So for inverse kinematic is what happened here is you are given the n effector position and orientations. You want to find the joint displacement. So the joint displacement Q1, Q2, Q3 to Qm. Q1 can be a prismatic joint or revolute joint. It can only be one. So it cannot be both. So for your assignment, you are going to draw the letter, for example, draw the letter O. So you may actually need to have some sample point, and then you may actually need to use the inverse kinematic to determine it. So this is the for transformation metric, it can actually be represented in this manner. So you have your nx, ny, nz, ox, oy, oz, ax, ay, az, defining the rotation matrix. And then you have your px, py, pz being the translation matrix. So in our context, this variable is always, the skew factor is always 1. So when you have, so your 0nt is equal to 0,1a, q1, 1, 2 multiplied by 1, 2a, q2, and so on. So this is your 0,1nt. So when you, and then every 0,1a can actually be generalized as I minus 1a, which is actually given in this form. So when you actually draw, so the inverse kinematic meaning that you have, when you are given with all this, when you're given with the transformation matrix, and then you're giving the n, the n effector position, ONT, you want to determine the joint angle. So you have this forward kinematics. So you compare them, just like you have the right hand side, the left hand side ij is actually equal to the right hand side ij, and I and j rows are row and common index. So if you actually look at it itself, you will actually find that if you equate them together, they're altogether 12 variable. So they're altogether 12 variables, 4 by 4, and then they're all together. Because 0001 is is a known variable, so you don't really care. So with that, you have 12 equations, and 9 equations will be for rotations, and we know that the rotation will only be involving 3 independent equations. So you rotate with the x, y, and z, and then you have the 3 equations for the position, which is your x, y, and z. So if you are going to solve for the n unknowns, so your q is equal to, the q being a vector will be q1, q2, q3 to qm transpose. Okay. With that, you can use a method called general analytical inverse kinematic formula. So the approach is essentially basically isolate one joint variable at a time. So for example, the first joint is q1, then I will try to determine q1. I try to isolate them first. So to isolate q1, if I multiply 0, 1, a minus 1 to the left and right side, I will essentially remove the first element. So I will actually end up start with 1, 2a, and then 2, 3a, and so on. So if you actually look at 1, 2a multiplied by 2, 3a, and so on, so this is essentially 1nt. So this is a function of q2 to qm. And this is a function of q1. So you look at the two-sided matrix, and then you look for the constant element in 1 over nt. Then you try to equate the left and right hand side, and then you solve for the q1. So the basic approach over here is you basically isolate one joint at a time. It's analytical. So there are numerical methods that have been researched, that have been used as well. But But the problem with the numerical method is that you may come to a situation where you don't have a solution. We'll talk about that later. So after that, you look for the function. You isolate the second set. So you have 1, 2a minus 1. So the 1, 2a minus 1 and 0, 1, a minus 1 is essentially a function of q1 and q2. So by doing so, you're actually reducing the right-hand side. So you end up with 2nt. So this 2nt become a function of q3 to qm. And this one become a function of q1 and q2. So you do the same thing. You look for constant element in 2nt. You equate the two left and right side. You solve for q2. Okay. So you keep going on and on. So there's no algorithmic approach that's 100% effective. So you may actually need to use a geometric induction to simplify the process. So you need to look at the geometric, and then after that use a cosine and sine thing in order to determine the process. Let me see, sorry. Okay. If you actually look at solving this this is become a nonlinear problem. So when you solve this nonlinear problem, the first thing they actually ask is, will there be an existence of a solution? So the existence of the solution meaning that the specific goal point must actually lie within the workspace. So if it's not within the workspace, you will not have a solution. So when you do the inverse kinematic problem in time, you're actually dealing with a work state problem. So when you actually talk about workspace, you have textureless, and then you also have the reachable workspace. So when you say textureless workspace, we're actually meaning that the particular space can actually be approached in all orientation. I think we have mentioned that in the first class. And then when we talk about the reachable workspace, the reachable workspace it can actually reach at least in one orientation. So as long as you can actually reach that particular point, it's your reachable workspace. So when you study your URF-IE that time, you actually find you don't really have a very big workspace. So when you want to draw the flow, it can't be too wide as well. So the textureless workspace will always be a subset of the reachable workspace. So there's a place that you can go, but the place that you can go will definitely include the place that everyone that can be reached in all ways. So if I consider a workspace of the two-link planar manipulator that we actually gone through earlier, so you have this joint 1, joint 2, this is L1, L2. If L1 is equal to L2, your reachable workspace will be a disk of radius 2L. So this is your reachable workspace. So the end point for this reachable workspace will be actually along this circumference. And so this is the end point. So this is a point that you can reach in various ways. So the textureless workspace will only be a single point at the joint 1. So for this single point itself, if you want to reach it in all orientations, so this way and then this way, this way, this way, and this way, we will actually be only the center points can actually do that. We need to know the concepts of textureless workspace and reachable workspace, because if a point that's actually at the textureless workspace, meaning that you can reach in all orientation, the chances of avoiding an obstacle will actually be higher. So the reachable workspace, meaning that you can only reach, if there's a workspace that you can only reach in one way, it will limit the solution that you have. So if what happens if my L1 is not equal to L2? So if my L1 is not equal to L2, I will actually end up with a ring. So the ring of the outer radius L1 plus L2 and inner radius L1 minus L2, the magnitude, absolute value. So there's no sign that's actually involved. So there's no textureless workspace. So you have no point that can actually reach in all orientation of the manipulator. So you may actually come across a situation where you have multiple solutions. So when we're actually looking at the redundancy, when we actually look at the inverse kinematics, we are actually looking at the workspace and redundancy. So the redundancy is defined when you actually have multiple solutions. And then in some cases, you might have infinite solutions. In example, in a kinematic redundant manipulator. So if you have a manipulator that has more degree of freedom than the desired degree of freedom, you tend to have a redundant. You tend to have the redundancy. So for example, for this single end effector position, you can actually reach in this way. You can also reach in this way with the planar RR manipulator. So there are some general notes that you actually need to take notes. So a manipulator arm must have at least 6 degrees of freedom to locate its end effector and an aperture point with an aperture orientation. So the UR5E robot have a 6 degrees of freedom. You need a 6 degrees of freedom. If the number of degrees of freedom is more than 6, you may actually end up with infinite number of solutions to the kinematic equation. So for example, our human arm, you have a redundant manipulator. Our human arm has 7 degrees of freedom. So, but we don't really have. In most cases, in almost all cases, we don't have this infinite number of solutions. So in practical situation, you have this physical constraint. So for example, the joint limit. So the joint limit will actually reduce the number of solutions. So when you actually look at the fact sheet of the UR5E, the time they will actually denote the joint limit. If the joint limit occurs, the workspace and or no number of solutions may be reduced. So this is number, and the number of possible orientation may also be reduced. So for example, if joint one can actually rotate from 0 degree to 360 degree, and joint 2 is only 0 degree to 180 degree, so they can't actually rotate freely in this manner, you may not be able to have this configuration. So from 0 degree to 180 degree, we actually imply the directions. So counterclockwise positive. So this is negative. Clockwise rotation is negative. So 0 to 180 degrees, actually you refer to this counterclockwise angle. So this is why this is possible and this is not possible, although the absolute angle is actually less than 0 degree, less than 180 degree. So remember the sign. And then after you have after you have the information on the workspace as well as the redundancy, and then the next thing here is you need to know whether it can be solved. So it's not very possible because it's non-linear. So the equation solving is actually non-linear. So you may not have a solution. So you can use numerical method. So for example, Newton interactive method. But the solution will be slow, and then after waiting for hours, and then you may actually end up that it doesn't converge. So you may actually have all these issues. We look at an example. So if I have, let's look at the example for this inverse kinematic of a planar arm. So this is the 3-link planar arm. So this is the 3R arm. So 3R arm comprise of this is the skeleton drawing. So you attach the frame, and then you attach the frame. So this is the base frame, and then you define your X over here. The Z-axis, the dot may be pointing out, pointing out, and then you can imagine that the Z-axis is actually pointing out. So this is your X0, Y0, and then you define your frame for X1, Y1, and X2, Y2. So this is the end effector point. So it's arbitrary 2 points. So you have a point over here, and then you tend to use it following the link. So you assign it as X3. So with X3, although it's a planar, you can imagine that all the Z is actually pointing out of the paper. So with all the pointing out of the paper, your Y will actually be over here. So although it's 2D plane, when you actually do the frame assignment and all those things, you can actually imagine a Z-axis that's actually pointing out. So this helps with the DH representation. So you derive the forward kinematic equations. So you derive the forward kinematic equation. You have your 0, 3, T, theta 1, based on theta 1, theta 2, theta 3, 0, 1, A, 1, 2, A, 2, 3, A. You multiply and simplify. This is what you have. Okay. So you start with, so after you have the forward kinematic equation, the next thing is you want to determine the inverse kinematics. So the inverse kinematic meaning that you want to find the joint variable theta 1, theta 2, theta 3 corresponding to a given end effector position px, py, and an orientation phi. So this is the orientation that you actually refer to for this particular point. Okay. So the working, I'll show the working over here. So you have your px. So you have your x. X is equal to px py phi. So this is your px. So if you actually look at your px itself, you will actually know that it's essentially your a1 cosine theta, which actually give you the angle, the value over here, and then a2 cosine theta 1 plus theta 2. That actually give you the distance here. And then finally you have your A3 cosine 1, 2, 3, which is your theta 1 plus theta 2 plus theta 3. So this will actually give you your PX. And then after that, your PY, which is over here, is essentially, so this is your X is determined by cosine, and then your Y will be determined by sine. So your Y over here, which is your this line, will actually be equal to A1's X1. This line, this distance will be A1, X1, 2, and then this distance will be A3, X1, 3, X1, 2, 3. So you actually end up with this. And then your phi angle over here, by studying the geometry, you will know that the phi is actually equal to your theta 1 plus theta 2 plus theta 3. This gives you the phi. So the first step of the solution is you need to determine the px, py, and phi given to you. So this is an expression. And then from this expression itself, so if you look at these two, your px is equal to this and py equal to this, they are nonlinear. So they are nonlinear. So, and then of course the orientation here is theta 1 plus theta 2 plus theta 3 is linear. But because this 2 is nonlinear, so this is nonlinear. You have to bear in mind that all angles measure counterclockwise, and the link length, I assume that they go from one joint axis to the next joint axis. So to find So once you have given the Cartesian coordinate of x, y, and phi, you have to find the analytical expression of the joint angle theta 1, theta 2, and theta 3. So same thing, you are going to solve them one at a time. So you define this position as a width. You define this position as a width. So this is your W. So this is actually holding on to your N vector. Connect to your N vector. So so from here itself, you look at the geometry, you will find that my PWX square plus PY square X will actually be equal to A1 square plus A2 square plus 2A1 A2 cosine theta. So this is known as the law of cosine. So after you have, from the law of cosine, you can actually determine your C2. C2 is your cosine theta 2. So if you look at this C2, there will only be a solution if this is actually between 1 and minus 1. So you set your x, you set your x2 equal to, your sine 2 is equal to plus minus 1 minus cosine square root. So cosine sine square, x2 square, x2 plus x, x2 square plus c2 square is equal to 1. So this is again another trigonometry rule. So from there, you can actually determine that your A2 is equal to arctangent to x2 at C2. So essentially what I'm actually doing here is I'm actually using a two-step approach. So I find the position of the width, and then after that I find the theta 1 and theta 2 from the W position, and then I determine the W3, the theta 3 from the W. So it doesn't actually mean that you will always be predicting. You have to study the geometry for the solution. So it doesn't mean that you always should start from theta 1, solve theta 1, then or solve theta 3 first, and so on. And then you have a set of trigonometry. So this is the value will be from minus 1 to 1. It's because minus 1 will be cosine minus 180 degree. 1 will be cosine 180 degree. So depending on your robot limit, you may not be minus 180 degree and cosine 180 degree. So you need to know the limit of your robot. So this is cosine squared theta plus sine squared theta is equal to 1. This is a trigonometry identity. Arctangent 2 meaning that arctangent 2 or arctangent 2's xy is basically convert the angle from Cartesian to polar coordinate. So your x is equal to r cosine theta, y is equal to r sine theta. Okay? Okay, so after you defining the width, you determine your theta 2, and then after that you can determine your theta 1. So you substitute your theta 2 back into your equation 2-4, which is this equation, and then you will be able to determine your theta 1. Because this set of equation is only depend on your theta 1 and theta 2. So after you have determined this is your sine theta 1, this is your cosine theta 1, you can determine your theta 1, which is your A tangent 2 sine theta 1 and cosine theta 1. So you find your theta 2, you find your theta 1, and then finally your theta 3, to determine the theta 3 is straightforward after you know theta 1 and theta 2. The phi is essentially your theta 1 plus theta 2 plus theta 3. So this phi is essentially your theta 1 plus theta 2 plus theta 3. So you can determine, you can derive your theta 3. So when you actually do all these inverse kinematic questions at time, you basically have to study the geometry and do the analytical method. But there's an approach over here, so you can solve the general approach, meaning that you solve one parameter at a time, equating them, and the other one is you identify the width. You differentiate the width from the arm. It will actually help you in solving the inverse kinematic problem. So there are alternate approach. So this is cosine theorem. So the cosine theorem, this particular point here, PWX plus PWX square plus PWY square is equal to your A1 square plus A2 square minus 2A1 cosine pi minus A theta 2. So if you actually sum it up together, it's actually cosine pi minus theta 2 is actually your cosine theta 2. So from there, you also can determine your theta 2. Yeah. Okay. And then but with this approach itself, it may actually give you, it will actually tell you they may be actually two admissible. In this case, there could be two admissible configurations. So this is one configuration, and then this is another configuration. Okay. Then after that, you move on to find the theta 1. Yeah, so the alpha this angle here is actually equal to A tangent to PWY over the common PWX. So you use a cosine theorem, you'll be able to find the beta. So theta 1 is actually alpha plus beta or alpha minus beta. So you can actually compute from here. Then, the theta 3 will be computed from the linear equation, which is your phi minus theta 1 and theta 2. So there are more than one approach of doing it by looking at the problem. Okay, we continue with solvability. So there are some theorems that we actually need to consider. So the first theorem actually say that a manipulator can be considered solvable if all of the set of the joint variable can be determined by an algorithm, which are associated with a given position and orientation. So this is solvable. And then the Asada will actually say that the kinematic structure for which a closed form solution exists is referred to as a solvable structure. So if you actually look at these two definition of solvable, the Asada 1986 one is actually a lot more tighter. And then the Asada 1986 will say that the closed form solution expressed analytically in terms of a finite number of known functions. In almost all cases, the industrial robot have a solvable structure. So most of the time, it should be fine. But you may be building your own robot, you may have your own arm and all those things. So like for example, the cable buying robot that I showed you earlier on. So the question here is it solvable for all kinematic problem is the issue that we need to look at. Okay. So a lot of time, for many applications itself, we simply use a robotic manipulator arm. So in industry, you see it. Yeah. But there are cases where you actually need to have a specialized robot. So these are the definitions of solvability. So if I have we mentioned earlier that a 6 degree of freedom manipulator arm is all that actually required. So a human arm with 7 degree of freedom is redundant. So for a 6 degree of freedom manipulator arm, the joint axis of 3 consecutive revolute joint will intercept at a single point, then the kinematic structure of the manipulator arm is solvable. So, like for example, when we actually look at the earlier on and the example of RRD, RRR manipulator. So you define a width there. The width point is actually the width have 3 consecutive revolute joints intercept at a single point. And then with that, you can actually know that the kinematic structure of the manipulator arm is solvable. But the reverse is actually not true, meaning that if you can actually solve the kinematic structure is actually solvable, but it doesn't necessarily to have this width. So the 6 degree of freedom robot have a closed form inverse kinematic solution if the 3 consecutive revolute joints intercept at a common point. So for example, those with a spherical width, the one that we've seen earlier on. And then the 3 consecutive revolute joints are indeed parallel. So for example, we look at this 6 degree of freedom manipulator with a spatial width. So if you are to draw the spatial width itself, it will be something like this. This is a revolute joint, so it will actually turn in this way. This is another revolute joint, so it will be turned this way. And then this is a revolute joint. It's a rowing. So this is row, this is pitch, and then this is yaw. So this is, you may view it in this manner. So the 3 consecutive revolute joints will actually intercept at a common point. So if you join the axis, you draw the axis down, and then they actually intercept at one single point. So by theory, this means that the structure is solvable. And then if it's solvable, you can actually safely move on to do the inverse kinematic problem. So the inverse kinematic problem can actually be broken down into sub-problem. So the broken down into these 2 sub-problems is actually known as the kinematic decoupling. The word decoupling meaning that you actually break them into 2 parts. So this is the width part. So you break this part from the arm. So this is a manipulator that we actually looked at earlier on when we first derived the DH notation. So this is a base and revolute joint. So this is one joint. This is a prismatic joint, and then you have another revolute joint. A revolute joint and a revolute joint. You define your width point over here. So this is your end. This is your 2 point. So your 2 point you define. So this is the 0 position, and then you assign the frame to the DH notations. So from here itself, you can actually see that there's a path P that actually go from the base to the end point, to the 2 point, the end effector point. And then there's a PW that actually go from the base to the width. So you define the width at the point where the axis intercept. So it's a lot simpler to work with the point W, which is at the intersection of the 3 terminal revolute joint, and then it can actually be treated as a position of the width. So the end effector. So you have the end effector position and orientation specified in terms of P. So this, as well as the rotation matrix. So when you have a rotation matrix 0,6 over here, meaning that you actually have the rotation matrix of the last point, the end point with respect to the base point. So it's actually comprised of these 3 unit vectors, N, X, and A. So this goes back to our earlier lecture on what is a rotation matrix. Comprised of 3 matrices, and each of these is actually a direction cosine. So your PW over here can actually be defined as your P minus the D6. So this is the D6 multiplied by the A. So this is your A rotation matrix from looking at this geometry. So if you do that, you will know that this PW essentially is a function of the three joy variable. You have your Q1, Q2, and Q3. And then one of them is a prismatic joint. It doesn't actually matter whether this is a prismatic joint or revolute joint. We'll take it as a Q. So you define this, and then the next thing is to solve the inverse kinematic problem, you will compute the width position PW as in this over here. So you compute PW. And then you solve the inverse kinematics for Q1, Q2, and Q3. So from 03T. So meaning that from the arm. So this is the arm, this is the width. So 1, 2, 3. So from arm and the width. So this is a non-redundant 3 degree of freedom arm. And then with that you compute the 03R from the 03T. So because you know the 03T transformation, you can pull out the rotation matrix. Then the 36R from 3 onward to 6 R will actually comprise of the Q4. This is the width part will comprise of the Q4, Q5, and Q6. So 36R is actually 30R multiplied by 06R. And then we know that the 30R is essentially the 03R inverse. The 03R inverse is your 03R transpose. So basically you don't need to do any modification from there. So you don't actually need to find the inverse, you only need to do a transpose. So with that you solve the inverse kinematic for orientation Q4, Q5, and Q6. So this is the procedure. Yeah. So if you're going to solve it manually, it will actually be going to be quite tough. So use a computer to help you. So you need to do this for your. You should do this for your CA, for your CA1. Don't do this. You can try and error. It will work as well. It may work as well. Try and error. You keep the different value of it's on your computer simulation. You give a different value of your input value. Then you can draw a circle. Okay. So in summary, we give the definition of position and orientation of the rigid body. We do an analysis of the different representation for the orientations. We work on the transformation of the coordinates. And then we determine the new position and orientation after a sequence of rigid body or motion. So we have been considering the rigid body. We are not looking at the soft body. Kinematic modeling of the robot manipulator. So kinematic modeling meaning that the spatial position and orientation of the end effector as well as the joint position, as well as the joint. Forward and inverse kinematics of the positions. Okay. Okay, we have some time. I'd like to give a brief. I'd like to briefly go through exercise 1. But for subsequent exercise, I'll not be going through them. Any questions? You'll be fast. So this is sample solution to exercise 1. I'm quite sure that the answers are right. Yeah, but there may be more than one way of doing it. So the first question on define kinematic workspace and trajectory is straightforward. So they are given in the notes. So basically, it's a reinforcement of the idea of these three concepts on kinematics, what is workspace, and what is trajectory. So in our last lecture for this, for the first half, will be about the trajectory planning. And then the second question, define frames and degree of freedoms. I believe everyone will be very clear now. So a frame is a coordinate frame. We are using a Cartesian coordinate frame, and then the frame will always be a right-hand coordinate systems. So right-hand coordinate systems, one way of looking at it is from x to y, and the time will actually give you x to y, the time will actually give you the z. So sometimes it may be confusing, could be quite confusing when you actually look at the 2D drawing of the axis. Because you're actually you're interpreting something from 2D to 3D, so it may be confusing, but in all cases, we should always do that. And then the question 3 is kind of, it's straightforward as well. So you have a vector AP rotate about ZA by theta and degree, and subsequently rotate about XA by phi angle, and then give the rotation metric the accomplished rotation in the given order. So so basically you have a point, and then you want to determine this rotation matrix. So there are two. So you have this. It's actually within a single frame. So it's something within a fixed frame itself. Things are straightforward. So you do the rotation accordingly. So they say that you first rotate according to Z, and then after that rotate about X. So you substitute in the matrix itself. This is what you have. Then the question 4, you have a frame B located initially coincident with a frame A. So this is the usual. So coincident meaning that they are actually perfectly aligned. So this is usually the thing that we actually first started. And then we rotate frame B about ZB by theta angle, and then we rotate the resultant frame again. So we're actually rotating with a frame that's in motion. So you are supposed to, same thing, we are supposed to give the rotation matrix. This is essentially something called Euler angle star rotations. So Euler angle star rotation, we have talked about the Euler star angle rotation before. So you have two consecutive systems, but the two consecutive systems, X, Y, Z, and U, V, W, should actually be initially aligned. So if you look at the rotation metric itself, it will become something like this. I think there's the question. Quite a few students actually ask about question 5. Actually, question 5 is not difficult at all. So you have this. You are given a configuration in this manner. The point to note is that you have your AC error. So meaning that you want to define your rotation metric that's describing C with respect to A. But we also know that the AC error is essentially comprised of 3 vectors. So you have your NSC, AYC, and AZC. So earlier on we are actually denoting it as MVW. NVW. So these are 3 vectors. So if you actually expand them out, each of these vectors is essentially a direction cosine. So it's a unit vector. Then you basically need to, all that you actually need to determine is you know the angle, and then you determine, and then you compute the cosine. So for example, if I'm to if I'm to look at the x itself, this is the XA, YA, and ZA. This is my XC. So if I determine the angle based on the cosine itself, I will actually say that this is cosine 90 degree, cosine 90 degree, cosine 180 degree. This is why I have 0, 0, 1. I do the same for the other set of vector. So once I have the other set of vector, I can form this rotation matrix. So this is ACR, so you have your 0, 0, minus 1, and the rest. So once you have that, you can you have, if the question may actually require you to have the ACR transpose multiplied by the P cone, the AP C translation vector. So this is what you have. Okay. So the part most of students will actually ask is, how do we actually come about this? So this is essentially from the first definition of rotation metric. And then question 6 is similar. So the same thing, you do it's a lot more tedious because you have this translation and you have the various translation. Yeah, but bear in mind that when you have something that's actually that's actually rigidly attached. So when you have something that's actually rigidly attached, meaning that you will be when you rotate the frame, the other one will just be rotated. So you work out, and then there's this post-multiplication and pre-multiplication that you actually need to be aware of. So this is quite a fair bit. Yeah. So bear in mind that the post and pre-multiplication rotation metric refer to transforming in new and global reference frame respectively. So you need to know this basically. So the 45-degree rotation angle on the right side is post-multiplying rotation metric. The 60-degree is the pre-multiplying rotation matrix. So pre-multiplying rotation matrix meaning that it's a transformation in the global reference frame. So if you take these two rules, basically, yeah, it will be applied across. So if you haven't worked on the problem, please start working on the problem. I'll be giving out exercise 2. So, and then after that, there will be exercise 3, and then after that, we will have the assignment. Okay? So this is good because without actually practicing, yeah, you will not learn about it. So you have the whole reading week to work on the solutions. I'm still trying to figure out how it can be done. So last year is done on luminous. So what the student had multiple try, and then I'll pick the highest score. But this may not be too good also because some students would keep trying all the different combinations. Which is not very right. Then the student actually have attended 20, 30 times for 10 questions. Yeah. So, yeah. Okay. No worry, I'll upload this handwritten stuff up. There may be problem. I may make mistake here and there on my working. So the same thing for question 7. Yeah, so it's straightforward. So you have this. The approach is very much similar. So make sure you have this ABT minus 1 is actually ABT transpose. So it's a homogeneous matrix. You do the multiplication, you will get the answer. So on question 8, in the solution that time I put example 1-9. So this is in the lecture note, chapter 1, kinematics. So you look at this example, okay? This is from the notes down there you'll be able to find. So basically this is the, you need to find the transpose of this. So this is this one minus this one, and then you'll get this one. And finally you have the unit vector. So unit vector, this is the definition of unit vectors. Actually, once you have this 1 minus 3, 2, then you basically just apply. Okay? Yeah. You need to try solving it, then you will appreciate what is going on. Any questions? So after today, you should be able to start working on your CA. So don't work until last minute, although you can actually submit at the end at the end of semester. So because you will make use of all the question that all the things that you actually learn. So as for the grading, I'm actually looking at your accuracy of your method. So if you solve the problem that I actually mentioned, so you got the power of the mark. And then the effort, the accuracy, the effort. So how good is your solution? And then the quality of your solution. So you can write, everyone can write the workflow, but some will actually do it nicer than the rest. And then you have to make sure all of them, all the different different letter have actually different stroke. They have to accomplish they should accomplish within the same time. So it's hard to be precise. Yeah. And then the last one will be your report. So try to write a good report. I'm not so concerned about your language, but it should be properly formatted. And then nowadays with the grammar checker and spell checker, it should be readable. And then Okay, so we'll end the class early today. Any questions? The team member meet one identical spot. No, the team member, once you contact your team member, you can actually meet anywhere. There's no, sorry, I don't have a lab for everyone. So you probably will have to meet. But MATLAB, you can actually, if you can download your MATLAB, please download your MATLAB. Please download a MATLAB on your computer to work on it. If your computer is too slow, in E2 there's actually a PC center, a computer cluster. So you can actually meet at the computer cluster, and there will be MATLAB there, and then you can actually work on that. Use a computer cluster, and then some of them you actually, if you have dash to the lab, you can actually work in the lab if you want. Okay. Any other questions? Okay, if no question, have a good evening. Thank you.